In this video, we'll continue our discussion on inference in simple linear regression by talking about how we construct hypothesis tests and confidence intervals to make inferences about the population intercept. Now, the population intercept inferences are going to be very similar to inferences on the population slope. So the sample statistic is going to be distributed normally. It's going to be unbiased. That is, the mean is going to be the population parameter of beta 0. And it's going to have a particular variance term, sigma squared sub b0, that we'll call it, where sigma squared sub b0 is sigma squared times 1 divided by n plus x bar squared over the sum of squares of x. Now, this doesn't need to be absolute value. This will always be positive. So you could just put parentheses around here. I think I probably had a typo between you and me when I was making this slide. So to test beta 0 equal to k, so this would be the null hypothesis, and then the alternative hypothesis would be beta 0 not equal to k, or greater than or less than, but typically not equal to. We would do very similar things to what we had. In fact, the test statistic is going to look identical, except it's going to be b0 instead of b1. Now we're still comparing to k, still dividing by the standard error. Now we're doing the standard error of b0, and the standard error of b0 is just the square root of the variance of b0. So sigma square root of MSE, remember that's the estimate for sigma squared, times 1 over n plus x bar squared divided by sum of squares of x. So you can see I didn't mess up it's not supposed to be absolute value, just put parentheses or brackets around it. So that's our standard error of b0. So we're still going to compare to a t-distribution with n minus 2 degrees of freedom, still going to do the appropriate critical value. Again, the software is going to get us the test statistic and the p-value, but again, these are calculated for comparisons to 0. To test a comparison against a generic k, then it's probably quickest to use a confidence interval. I mean, we can do manual calculations, but again, we mentioned in a confidence interval, we just calculate the confidence interval, and then we look at, is the parameter inside the confidence interval? Is it not, is the hypothesized value inside the confidence interval? If so, we fail to reject the null hypothesis. Or is it outside the confidence interval? In which case we would reject the null hypothesis. Now, it's important to mention, because in the next video we're going to talk about additional confidence intervals, that when we're talking about a confidence interval, what we're talking about is the confidence of blank. We're talking about the confidence of something. So in this particular case, in the previous case when we were talking about beta 1, we made a confidence interval for beta 1. In this case, we're making a confidence interval for beta 0. We're 95% confident that beta 0 is in that interval. So confidence interval is an interval where we're blank confident that the true value is in that interval. But because of that, we have a blank value is in that interval. That means we can calculate confidence intervals for different things. So I don't want you to get confused when we talk about confidence intervals in different contexts, because confidence interval is like a method, but we can apply that method to multiple different types of statistics. So when we talk about the confidence interval for beta 1, there's a 95% chance that the true value of beta 1 is inside that interval, or we're 95% confident that the true value is inside that interval. If we ran that interval a bajillion times, 95% of those would contain the true value. For beta 0, we are 95% confident that beta 0 is inside this interval, not b0, the sample statistic. That's going to be inside the interval 100% of the time. But beta 0, the population parameter that we have no idea what this is, or we have some idea, we're 95% confident that it's within this particular interval. So don't get confused on confidence intervals. It is something that sometimes throws students for a loop, but a confidence interval is for something. And in this case, this confidence interval is for the population intercept beta 0. All right, so just like before when we were talking about how we do interpretations of beta 0 or b0, remember, if x equals 0 isn't in the sample space, so this is all the possible meaningful values of x, then inferences about it may not be particularly meaningful. So if x equals 0 doesn't make sense, then inferences regarding it don't necessarily make sense either. And this is echoed for tests, right? We talked about it earlier with interpretation, but remember, as we talked about in previous videos, the statistical tests impact interpretation. And because statistical tests and interpretation are so closely tied together, this concept from our interpretation, if x0 isn't in the sample space, inferences may not be meaningful, still applies when we're talking about statistical tests. All right, so you'll occasionally hear the term robust. Robustness roughly refers to a statistic's validity when assumptions aren't met. Now, we haven't talked about assumptions. We will, in the next lecture, talk about the assumptions that are made in order to fit these models, and some of them will make sense, some of them will make more and less sense. But as a general rule, the term robust describes how statistics function under assumptions that aren't necessarily met. So one of the assumptions are that the errors are normally distributed. You saw that when we talked about the distribution of B0 and B1, that those were distributed normally. We're assuming that they're distributed normally. And in cases where that's not quite true, we find that these are still pretty reasonable. So this is the idea of robustness, is that even if this isn't particularly true, we can still count on the validity of these statistics being right, and these are called robust to this particular concern. So if we only have this being a little bit not true, so a minor violation of this assumption, then this is okay. Definitely come back and review this slide as we're talking about assumptions in the next lecture, because this is an important component to consider when we're talking about statistical assumptions. We're mentioning it here because we've already implied some of these normality assumptions in talking about the distribution, but it's important to say and to note that even if this isn't 100% true, if it's reasonably close, that is, if there's only a minor difference, then these tests still maintain their validity. And we will talk much, much more about this in the next lecture. All right, so for a quick recap, our model is y equals beta 0 plus beta 1x plus epsilon. This is the population model because we're using betas and epsilons as opposed to b, and we don't even have an epsilon if we're looking at a predictive value. The errors are normally distributed. The errors have a mean value of 0, and the errors have a variance of sigma squared. The y's are also normally distributed. The mean of the y's, this is y hat, but it changes depending on x. This is the line. So what we're saying is that the y's are centered on the best fit line, beta 0 plus beta 1x. And the y's have a variance conditional on this fixed model of x of sigma squared as well. Now for the parameter estimates, we already wrote these down. In fact, you probably already have all this written down. This is a recap, but sometimes it's nice to have it all in one place. Parameter estimate for B1 is the sum of squares of xy divided by the sum of squares of x. Parameter estimate for B0 is y hat minus B1 times x, or excuse me, y bar times minus B1 times x bar. And the parameter estimate for sigma squared, the population error variance, is s squared, or the MSE, which is the sum of squares of error divided by the degrees of freedom for the error. Or again, recall sum of squares of error, sum of squares of anything, is just that value minus its mean, quantity squared. So that is the residual squared. Recall that the mean is 0. So this value minus its mean is just this value, quantity squared. And then divided by the degrees of freedom, we're estimating 2 parameters, beta 0 and beta 1, so it's n minus 2. For the confidence intervals, for beta 1, we recall that this is the confidence interval for beta 1. We use B1 in the confidence interval for beta 1. And these are both pretty straightforward. For beta 1 and beta 0, it's just the parameter estimate plus minus the critical value times the standard error. Pretty straightforward, where we have the critical value as 1 minus alpha over 2, and then n minus 2 degrees of freedom. For the significance tests, to test against a generic k, we have b1 minus k divided by the standard error. and that's distributed as a t-distribution, then minus 2 degrees of freedom. Again, we use whatever alpha is appropriate under the null hypothesis. And again, this is distributed under the null. We use the null hypothesis when we're making decisions about statistical significance. So these distributions are made under the null. We look at the probability under the null. Recall our coin example. This should make some intuitive sense. Well, at face value it doesn't, but then if you think about the coin example and you think about why don't I think it's a fair coin, and you realize, well, it's because if it were a fair coin, then I better go buy a lottery ticket because that was the most unlikely thing ever to happen with a fair coin, then you realize that actually we do tend to make these kinds of decisions under the null hypothesis. Okay, so for the significance test for the intercept parameter, population parameter, we have beta 0 equal k versus the alternative, that's the null, versus the alternative beta 0 not equal to k. Test statistic is the exact same as the test statistic for the slope, except we plug in beta 0 or b zeros for b1s. And then for all these we get a p-value if we use software, and if the p-value is less than the alpha for that particular problem or for that particular test, then we reject the null hypothesis. So this video we talked about inferences regarding the intercept parameter, and a quick recap of all of our materials: the significance test, the confidence intervals, the model, and the parameter estimates for everything that we have gone through thus far in just a couple slides, so that it's all in one place for you.